Welcome to Spring LIB.
Hi there. Today we're going to be working on a problem that is a mass on a spring. The problem gives us the value of the mass, 1.5 kilograms, and the position with respect to time. From this, we're asked to find a lot of different things, including the period, spring constant, the maximum velocity, the maximum force, positions, times, and accelerations. So the first thing that we want to do with this problem really is in green I've written down the position with respect to time, the general equation for it. We want to look at the two and kind of notice the similarities between them. So we can pick out right away that 7.4 centimeters is going to be the amplitude and 4.16 is going to be that angular frequency. Right away, we can also take a derivative of x with respect to t to get the velocity. So we get v of t is going to be equal to negative a omega times the sine of omega t plus phi. If we look a little bit further ahead in the problem, we know that we're also going to want to be looking at the acceleration. So we'll go ahead and do the general form for that as well. So the acceleration with respect to time is going to be equal to negative a omega squared cosine of omega t plus phi. So now we can jump right in, now that we've got kind of this general stuff out of the way, and get right into the problems. So part A is asking for the period. We know that the period is going to be equal to 2 pi divided by the angular frequency, omega. From looking kind of at the general to the regular position equation, we can see 4.16 is omega. So we just kind of plug in all those numbers, and we get that t is going to be equal to 1.51 seconds. If we look at part B, we're going to look at the spring constant, K. Now, K we get from an equation that we've got omega equals the square root of K over the mass. So this is really why this mass comes in handy. We solve that for K. K equals the mass times the angular frequency squared, which is about equal to 25.96 newtons per meter. Always important to include the units and know which units you're talking about. Looking at letter C, we're looking at the maximum velocity. So if we go over to the green equation for velocity, we have velocity with respect to time is equal to negative amplitude times angular frequency times some sine function. We know that the most a sine function can be is ranging from -1 to 1. So we know the maximum of this is going to be at a times omega. So we say V max is going to be a omega, which is going to be approximately equal to 30.78. Now, this 7.4 it's specified in the problem for the amplitude is in centimeters. So this is in centimeters per second. If we look at part D now, part D, we're looking at the maximum force. The quickest way to do this one is looking at just the equation for force for a spring. So F equals negative K times X. We can see that the amplitude for X is 7.4, which is also the furthest that it's going to reach. We can look at K, we've already solved for, is 25.96. The important part of this, though, is that 7.4 is in centimeters, and we want it in meters. So you have to drop down a couple decimal places. But once you do that, you end up with 1.92 newtons. If you forget to change from centimeters to meters, this is not the unit that you'd be in newtons, which is important to remember and important to look at. When we move to part E, it's asking for basically just the green equations that we have over here with the t's. We're putting in 1 second, t at 1 second. This equation is pretty standard, plugging in numbers and solving. Because we have kind of all these forms over here, just break out your favorite calculating tool and go ahead and solve for x at 1, v at 1, a at 1. What you should get when you've done all that is that x at 1 is negative 1.25 centimeters. V at 1 is equal to negative 30.34, and this is centimeters per second. And then the acceleration at 1 is going to be equal to 21.57 centimeters per second squared. So that's part E is pretty easy. It's just plugging into the equations that we already have. Part F we're looking at is another one that's a lot like part D, where we're looking at the force at 1 second. So to do that, we use the same equation that we used in part D, where we've got the force is equal to negative K times X. The negative sign is a convention choice, but because the force is always going to be pointing away from the direction that the X is why we've got that negative there. This is going to cancel with the other negative that we have. And if we remember to change from centimeters into meters, then we have force is equal to about 0.33 newtons. So that's how you go about doing this particular spring mass problem. I hope